welcome to writing nuclear decay equations. Writing nuclear decay equations have a set of steps that we're going to follow. You're going to start by writing your starting isotope. We're using isotopic notations where we include both the number of protons, the atomic number on the bottom, and the mass number on the top. Next, you're going to find the decay mode using reference table N. You write your starting isotope on the left side of the arrow, and then the decay particle on the right side of the arrow, and then we're going to actually do a small minor calculation to determine what our ending isotope is going to be. And we do that by balancing for mass and for the number of protons or the atomic number. And this will require us to look in the periodic table. Be sure that you are being really careful and watching out for paper cuts as you proceed through these problems. You're going to be doing a lot of flipping around. First one we're going to do is the decay of francium-220. Francium-220 is an example of an alpha decay, which I'm telling you in this problem, but you can also find that out by looking at reference table N. So francium-220 is written like this with our mass number on top. You're going to then go to the periodic table and find the atomic number for francium, which is 87. Our alpha particle can be written with the little alpha symbol and a 4 on top or a 2 on bottom, or you can write it as a helium nuclei. So we're going to start with our starting isotope, which is 220, 87, Fr. Then we always have a little arrow indicating that this is decaying, so our kind of reactant in this case is francium-220. Our decay particle, we write first, then a plus sign to show our other product, which in this case, so because we have 220 up here, this is like an equal sign in math. This is like 4 plus x over here. So really what happened was we had a total mass of 220. We lost 4. We had an ending mass of 216. On the bottom, we started with 87 protons. We set this up like a problem in math. This would be like 87 equals 2 plus y. So we started with 87 protons, we lost 2 in our alpha particle, and we ended up with 85 protons. Next, we're going to go to our periodic table. You find number 85, which is astatine. We always got to check ourselves, make sure that your masses equal up. So if I look at my masses here, I've got 220 equals 4 plus 216. That checks. 87 equals 2 plus 85. That checks. I'm good to go. Next, what we're going to do is a beta decay, or gold 198. We're going to go to the periodic table to find out that gold's atomic number is 79. Either of these ways of notating a beta particle are fine. Just make sure that that bottom number is a negative. And again, that's from table N. So our starting isotope is gold 198. This is going to go ahead and lose a beta particle to give us a resulting isotope. Now, a beta particle has negligible mass. In terms of the amount of mass that it loses, it doesn't actually show up in this reaction. So our gold 198, we're really subtracting a mass of 0. We're ending up with a final isotope that has a mass of 198. Now, some mass was lost, but it's just a very small decimal, so it doesn't show up in this reaction. So really, this is like 198 equals 0 plus x. X equals 198. On the bottom, we started with 79 protons. In this type of decay, a proton turns into a neutron. So really, this is like 79 equals negative 1 plus y. So it's like we're subtracting a negative, which then becomes adding. So if we were to actually solve this equation, we'd find that y equals 80. So since a neutron turns into a proton, we actually end up having more protons than we started with. So our gold actually decayed into mercury, which is bad news because mercury is a liquid, and bad news because it's poisonous. So let's check and make sure that everything added up correctly. 198 equals 0 plus 198. Check. 79 equals negative 1 plus 80. 80 minus 1 is 79. They check. Last but but not least, there's positron decay. We're going to write the positron decay for iron 53. Now, positrons have very similar notation to beta particles, except for the slight difference that the bottom number is written as a positive one. And it is important to show that sign and really differentiate this from a typical beta particle. So iron 53, again, this has 26 protons, which you find on the periodic table, is going to decay, and it's going to give off a positron. And solve for what our resulting isotope will be. Positrons have negligible mass, just like beta particles, so our mass on top is going to remain 53. On the bottom, we had 26 protons. We're actually turning a proton into a neutron here. So this is 26 equals positive 1 plus x. In other words, x here equals 25. So we do 26 minus 1, and we end up with 25 protons. And this gives me manganese from the periodic table. So 0 equals 0 plus 53. My mass is checked. 26 equals 1 plus 25. My numbers of protons checked. For gamma decay, gamma particles actually don't release any mass. So since gamma has no mass and no charge, very often these go along with other types of decay. So here we actually have an alpha particle accompanying this gamma radiation, but as you can tell, there's actually zeros here, so this doesn't actually cause a transmutation per se, and doesn't really affect our overall balancing of the reaction. Here's a few for you to try on your own. Remember, the first thing that you're going to do is you're going to look up your initial starting atomic masses. Please take a minute and pause this video while you do so. The answer for the first one, which is an alpha decay, we have an initial starting isotope of plutonium. Plutonium's atomic number is 94. This is giving away an alpha particle, so we go from 239, we lose 4, we end up at 235. 94, we're losing 2 protons from our atomic number, we're ending up at element number 92, which is uranium. For our neon decay, neon has an atomic number of 10. Neon decays by positron decay. We have no change in our mass number. We used to have 10 protons. Our ending isotope will only have 9 protons. So keep in mind, what we end up having here is 10 equals positive 1 plus x. So our x down there is 9, and that tells us that we have element number 9, or fluorine. Beta particles can often be the most confusing to people because of the negative. So we have strontium, which has an atomic number of 38. Strontium, because it's losing a beta particle, has almost no change in mass. So our top number with our product is still 90. On the bottom, what's really important to keep in mind, we had 38 protons that we're starting with. The reason that a beta particle is written as a negative 1 is we actually have a neutron turning into a proton. So if you solve this mathematical equation, you'd really be adding a negative 1, subtracting a negative 1, which is adding. So you would get x equals 39, which is why our ending atomic number right there is 39. In other words, we have 39 protons, which indicates yttrium. And if you wanted to try to figure out your missing species at the bottom, start by finding out that boron has 5 protons, beryllium has 4 protons. So since we have 8s for both of these guys on the top, we gotta have a 0 here. We have 5 starting with our boron here, so we have to have a positive 1 on the bottom